Welcome back to my lecture on demand-driven analysis. So here I want to briefly recap something that I already briefly also mentioned in DECA 1, and this is the notion of unbalanced returns. So remember that normally in a context-sensitive analysis, we always want to have balanced returns. So we want to match returns with their respective calls in particular, right? So that's exactly what gives us context sensitivity. But in a demand-driven analysis, there can be situations where that is simply not possible. And that is because a demand-driven analysis is typically an inside-out analysis, and that sometimes requires unbalanced returns. So to explain this, let us consider this minimal example here, right? So we have a main method that's maybe doing some taint analysis, tracking the secret. And there are a couple of calls to this identity function here, but there are also a couple of calls to this foo function. And here we are actually leaking the secret to foo. Here we are not. We are just leaking some other constant. And then foo itself, we assume, has some sync method here, right? That's actually leaking this to the outside. And now let us assume that we actually now want to search backwards from leak to find all possible inputs. So here we're not doing a regular forward taint analysis, but we're actually doing a backward taint analysis. And here that means that we are actually starting not just at the end of the program, so to say, within this call to foo, but we are also not starting at the top of the call stack, right? So we're not starting at the program's entry point. We're not starting within main, but we're actually starting down in this call to foo. And then we're starting in particular at this leak call. And now we want to do a demand-driven analysis to find out what value could have been assigned to V here, okay? And if you now look into this, you will notice that here we actually have the situation of an unbalanced return without a call. Why is this? So if you really assume that this is the first statement that the analysis is really considering, all right? So it may have done a syntactic scan statement by statement through the program. It may have determined that this is a sync statement and that's where the analysis should start, but the analysis doesn't know anything else, right? Then in particular, at this point, it will not yet have any calling context, right? It will not have a call stack, and the analysis doesn't know whether it came from here or it came from there, because that's where we start, right? We start down here. And that can be problematic, right? Because as you can see here, we actually have a secret value at this call, but we do not have a secret value at this call, okay? So to some extent, we want to be able to distinguish these calls, and also in particular, we need to distinguish these identity calls, because otherwise we would be conflating contexts. But here, yeah, well, we can't really solve this problem, right? We have no context here. But the point is, at this point here, that's actually fine, okay? So here we have no chance but to return into all these possible callers. So the analysis will actually return to just before this foo call and to just before this foo call using an unbalanced return. That's okay. That's how demand-driven analysis work, okay? But then the analysis, it progresses further, right? So in particular, it will propagate this T value further up here into this identity call, and it will propagate this S value further into this identity call. And now something important happens, because this backward analysis it must process balanced calls when itself enters new callees. And that's exactly the case here, right? So we will go backward, and then we will enter this identity call. So we will actually push this call side onto the stack, so to say, right? And the same happens here. We push this call side onto the stack, okay? And then we are analyzing this identity call here. And what's important now is that because we now keep track of the call stack here, we can match this return against this call So we basically label these edges here with the call side like we normally do. And likewise here, right? So this means we can distinguish this call and its return value from this call and its return value. And that's sufficient, right? So that then actually allows us to distinguish sufficiently these two different calling contexts. And in particular, it lets us determine that we can have a data leak from here through this call, through foo to here, but actually no data leak down here, right? In particular, this call here is not involved in the data leak. So there are unbalanced unbalanced returns at first, but whenever the analysis re-enters some new call site, it builds up a call chain, a calling context, and that allows it to actually match the corresponding returns as it goes. So just as a rule of thumb, you have an unbalanced return where no call stack exists already. But nonetheless, we build up a call stack at calls and match against it at corresponding returns. And so in this case here, you would basically have first an unbalanced return from foo. That's what we are seeing here. But then as we are entering a call again, this return here, it must match this call, right? So there's some unbalanced returns at first. And then here, any call that we do process, it must be matched again by the corresponding return. Okay. And there's a second technicality that I also need to discuss with you because that's equally important. And that's the necessity to correlate contexts. And that's important because whenever you're using a demand-driven analysis, and actually also it can also be important for exhaustive analysis, but for demand-driven analysis, it matters in particular. We need to make sure that the analysis are considering the same context, actually. So in general, of course, we desire interprocedural analysis to be context sensitive, right? You know that. And of course, we do not want this to change just because we execute the analysis in a demand-driven style, right? So also demand-driven analysis should be context sensitive. But we need to take care to actually preserve context sensitivity, in particular when we're combining multiple analyses with one another. And I've already shown you these scenarios, right, where we are having, let's say, a taint analysis or any client analysis for that matter, that uses a pointer analysis, right? But also a pointer analysis itself, it might again use some constant propagation, let's say, to resolve reflective calls, right? Or it might use some core graph analysis to actually resolve virtual function calls. So in general, you can have any number also of demand-driven analysis that call one another, right? So this indirect recursion that I talked about, that does not need to be restricted to a single backward and a single forward pass. In realistic analysis, you can have a dozen or so different analyses that all call one another in one big demand-driven fashion and in one big fixed point iteration, right? And that doesn't make it simpler, but that makes it even more important to take care of this context sensitivity problem. But let me show you a relatively simple example first. So again, let's assuming we're doing a taint analysis, and here we are assuming it's a regular forward taint analysis again. And then we are also later on going to be using a demand-driven pointer analysis. So here we are having two different calling contexts of this method foo, right? So we call foo here and we call foo there. But these two contexts have been designed in a particular way, namely here we are actually passing a taint to f. Okay, so here we have a taint in this third parameter, but we have no aliasing between the first two parameters. Okay, here they're not aliased, they're definitely pointing to different objects. And this context is exactly the other way around. So here we are assuming that z is a non-tainted value, so this doesn't matter really to the taint analysis. But here, these two parameters, the first and the second, they are aliased, okay? And now you can imagine if we were to conflate these two contexts, right? Assuming that here we have aliasing and attained, and or here we have attained and aliasing as well, then that might be problematic because then we might also think that in this particular context here, or in this particular context here, we might actually reach the sink, which is not actually the case, right? So the sink can never be reached in this program because in situations where S and therefore A.F is tainted, A does not alias B, right? So that's this context. And in the other context here where A and B are aliased, we don't have attained, okay? And therefore, there's no data flow here, right? So you can never have a data flow from this statement or this statement to the sink, or at least no tainted data flow, right? And so, yeah, we want to avoid these sort of false positives that you would otherwise get, right? But normally, you would have the situation that you have attained that's being assigned from F to S here, right? And now the demand-driven pointer analysis again at this point would be raised with a query of may aliases of A, okay? And now the alias analysis would search backward, right? So it would see, okay, how is this parameter for A actually initialized? And like I told you, if you now assume this is an unbalanced call, right, an unbalanced return, then you would actually search backward for all the different allocation sites also in this context, right? So it would search not just here, but it would also search here. And it would find this allocation site here. And using the forward propagation, it would then see that in this context, you can have aliasing between X and Y. Okay, so that means in the callees context, you can have aliasing between A and B. But that's now giving you a false positive, right? Because now the alias analysis tells you, yes, A and B, they can be aliased. And then the taint analysis that actually raised the query, it will assume that A and B can be aliased, and it will propagate this taint to B.F, and it will alert the user that the sink can actually be reached. And that's problematic, right? That's giving you a false positive, and that's one that we do not want. And the problem here is, again, that we process this return as an unbalanced return because there was no call stack yet by the pointer analysis. But the point is we should have used another call stack, namely we should have used the call stack by the taint analysis, right? So we should have used the information that the taint analysis is coming from this calling context, and we should have injected that context into the query that we raise in the pointer analysis. Okay, and that's actually exactly what the right approach would do, right? So here, instead of getting this answer that A and B may alias, we want to make sure that we synchronize these contexts so that these false positives can actually be avoided. So the lesson learned from this is to maintain context sensitivity, one must synchronize, one must correlate these contexts between the different analyses. And here the pointer analysis in particular should visit only those contexts which actually matter to the client analysis, so here to the taint analysis. All right. And that's really important. And so for instance, in Boomerang, if you look at how this has been implemented, I'll explaining that to you still in more detail later. But basically, there's an API, right? So when the alias analysis in this particular, so Boomerang itself, when it actually processes a return, it will call back to the taint analysis, asking the taint analysis which context it should actually return to. So there's a two-way communication protocol that has been used to actually facilitate exactly this correlation or synchronization. that's all I wanted to tell you about the technicalities about demand-driven pointer analysis. So the handling of context, it's really important to make this both efficient and precise in particular. And in the next video, I will be talking about a bit more of a theoretical result, which is that demand-driven analysis cannot only be more efficient than an exhaustive analysis, but as has been shown by these authors, it can actually be even more precise. And that's really exciting. So we can even get more precision than by the most possible precise exhaustive analysis you could ever think of.